My name is Jonas and I welcome you to this video in which we will look at transmission ratios and how we can use them to reduce our system to the input or output side for our control algorithms. When talking about transmission ratios, we often think about motors and gearboxes, but this is only a part of the whole story. In engineering, transmission refers to the process of converting a value of a physical quantity into another value of the same quantity. It can therefore be viewed as a transfer function. The formulas to calculate the transmission ratios for three of the most common mechanical solutions used in robotics are shown. Note that usually the torque or force gets amplified on the cost of a reduced velocity. We can use the transmission of a physical quantity in our control algorithms. That allows us to choose whether we want to express the controller in terms of the input side or output side of our system. If we take a motor with a gearbox as an example, we can express our controller in terms of the gearbox input or gearbox output. Both options are used and can be viable. However, to be able to interpret our control variables from a physical point of view, we should express our controller in terms of the output. Obviously, it is a lot simpler to understand what happens if we apply a torque of 1 Nm on the output shaft than if we apply a torque of 0.1 Nm on the motor side. In either way, we have to reduce our physical quantities to one side. Let's take the motor with the gearbox from before and apply a load on the output shaft. The motor has an inertia J1 and the load J2. We can then reduce the inertia to either side by multiplying or dividing it with the square of the transmission ratio. The same can be done for the velocity and torque by multiplying or dividing them with the transmission ratio. Even though this topic is rather trivial, it is very important and often forgotten. We will now look at our mobile robot and how we can reduce its mass to the output side. On the robot, we have a motor with a gearbox to which a wheel is attached. The total transmission ratio can therefore be calculated as the transmission ratio of the gearbox times the transmission ratio of the wheel. The transmission ratio of the gearbox is directly out of the datasheet, while the transmission ratio of the wheel is 2 divided by the wheel diameter. A good approximation for the mobile robot is that half the mass of the robot is on each wheel. Further, we have to consider the inertia of the motor, encoder and gearbox. These three values are given as 1 in the datasheet of the motor. We therefore get the total mass per wheel as half the mass of the robot plus the motor inertia times the transmission ratio squared. However, we have to be careful in this case. If the teeth of the gearbox are engaged, then our calculations are correct and the controller feels a mass of 0.276 kg. But if the teeth are not under load and the movement is in gear backlash, then the controller feels only the mass of the motor, which is 0.046 kg and thus 6 times smaller. To deal with this, we can make a conservative approach and say that the total mass of the robot is always just 0.046 kg. Another way would be to detect whether the teeth are engaged and change the mass accordingly. Or we can also define the mass to be 0.276 kg and live with the slight noise that the motor produces during the short period of time it is in gear backlash. Thank you for following me through this video and I will see you in the next one.